in a straight line, I had a solid figure in my hand. So, I had two intersecting planes, which are plane M and plane N. So the question is, where do they meet? As you can see, of course, they meet in a straight line. So therefore, theorem 1 is always true.
Don't drop that hey, don't drop that don't drop that don't drop that
Theorem number 2. A plane can be determined by first, a line and a point plotted in. Second, two intersecting lines. Third, two parallel lines. A plane is said to be determined by certain elements. If this plane contains these elements, while no other plane does contain them. The plane is said to be determined by certain elements. If this plane contains these elements, while no other plane does contain them. We say that 3 non-collinear points determine a plane, while any number of collinear points fail to determine a plane. 2 points determine a line, and it is obvious that 2 points do not determine a plane. To prove that theorem is true, I have this solid figure. To prove that theorem 2 is always true, I have this solid figure. First, a plane can be determined by a line and a point not on it. As you can see in this figure, this is your line, your given line, and your point. Can this determine a plane? Yes. Can this determine a plane? Yes. So moving on, stated in theorem 2, corollary 2, a plane can be determined by 2 intersecting lines. Where do you think Theorem 2, corollary 2. A plane can be determined by 2 intersecting lines. In this figure, the 2 intersecting lines, this line and this line. So, it can determine a plane. It can. Theorem 2, corollary 3. A plane can be determined by 2 parallel lines. In this figure, there are 2 pairs of parallel lines. This line, this line. The other pair is this line and this line. Then these parallel lines determine a plane.
Don't drop that hey, don't drop that don't drop that don't drop that
Theorem 3. If a line is perpendicular to each of 2 lines at their point of intersection, it is perpendicular to the plane of these lines. This is your figure. Given a plane, this is your plane. And 2 lines lies on a plane. This is your 2 lines. Then a normal to the plane. A normal to the plane is a line perpendicular to a plane. As you can see in my figure, the 2 line crosses the point of intersection. And this line is perpendicular to the plane of these lines. So therefore, theorem 3 is always true.
Theorem number 4. Through a point, there is one and only one plane perpendicular to the line. To prove that theorem 4 is always true, I have here this solid figure. Given a plane, a line, and a point. If you extend this plane, imagine that this plane is extended. Given this point and this line, there could only one line that is perpendicular to this plane. Got it?
Theorem 5. Through a point, there is one and only one line perpendicular to a plane. You are given a figure. As you can see, this is your plane figure. In a plane figure, you can see this line. If you extend this line, you will have this line. Between these two planes, you can see a point. So therefore, through this point, there is one and only perpendicular line. So this is your line, this is your point, and this would be your another line. So therefore, I conclude there is one and only line perpendicular through a point.
Don't drop that da-da-da. Hey, don't drop that da-da-da. Don't drop that da-da-da. Don't drop that da-da-da.
Oblique lines from a point to a plane, meeting the plane at equal distances from the foot of the perpendicular are equal. And conversely, two equal oblique lines from a point to the plane, meeting the plane at equal distances from the foot of perpendicular. To prove that Theorem 6 is always true, I have here a plane, a normal to the line, and two oblique lines. To prove that Theorem 6 is always true, given a plane, two oblique lines from this point, and a line that is perpendicular to the plane, which is the normal to the plane. If oblique lines is perpendicular to the plane, these two oblique lines perpendicular to the plane. If oblique lines from a point to a plane, meeting the plane at equal distances from the foot of the perpendicular. This is your point of the perpendicular, the point of the normal line, the point where this line and this plane meet. Therefore, Theorem 6
Don't drop that da-da-da.